a soutenu sa thèse en 2006 au corps à l'université UCL de Louvain, sous la direction de Laurence Rousset, et en parallèle, il a fait une thèse aussi à l'Académie russe des sciences, avec Alexander, Alexander Lazarev. Il est venu en France à la suite de sa thèse pour être en postdoc au LIX où il a travaillé avec Philippe Baptiste, et ensuite il est depuis chargé de recherche à l'Inria où il est au sein de l'équipe Realopt. Alors l'équipe Realopt vient de changer de nom, elle s'appelle maintenant Edge, et qui se réunit dans les locaux de l'université de Bordeaux, plus exactement à l'Institut de mathématiques de Bordeaux. Alors Ruslan, tu as travaillé avec des chercheurs premier plan, tu as souvent traversé l'Atlantique pour des collaborations internationales et des projets de grande envergure. Tes premiers travaux, c'était plutôt en scheduling à l'origine, avec de plus en plus d'algorithmique et de plus en plus de programmation mathématique, et puis maintenant tu es un grand spécialiste de la génération de colonnes, et à la fois par la théorie et de grands articles, et je vous incite à feuilleter ou lire son HDR, c'est vraiment très instructif et très pédagogique, et puis de grandes publications, et aussi un très fin codeur qui nous a proposé à tous des codes où il a participé en cheville principale et en concepteur, que ce soit Babcode, Coluna, et puis aussi un outil qui lui est, pour ces outils qui sont à la fois très efficaces et génériques, et puis un outil ces derniers temps VRP Solver qui permet de résoudre des problèmes de tournée de véhicules pour plein de variantes à l'intérieur de ce code. Alors voilà, Ruslan, tu vas nous parler d'un sujet qui me tient à cœur en ce moment personnellement, les coupes non robustes.
Yeah, thank you, Claudia. So I prepared my presentation in English, so if you don't mind, I would like to speak English here. And so I will, so the time is not very big, so I go straight to the outline of my talk. So after small introduction, I will do a reminder about branch cutting price, and then I will make an overview of several ways to obtain non-robust cutting planes, and then I would like to speak a bit about the issues which may arise when you are using non-robust cutting planes, and then I will finish by some takeaways. So I would like to start with this reminder about the MIP solver. So probably all of you know that the MIP solvers are very efficient nowadays. So I picked this slide from one of the producers of one of MIP solvers, and they list the industries from which the clients come, which use MIP solvers, and you can see that MIP solvers are now widespread everywhere. They use it pretty much, and I think there are two main reasons why they use it so much. First is that they are accessible through modeling. There are now a lot of modeling tools which are available to use them, and second, that these solvers are very, very efficient. So to illustrate that, I picked another slide about the progress of MIP solvers in recent years. So from 91 to 2015, there was 1 million, so MIP solvers become on average 1 million times faster. So they're now very, very efficient. But still there exist some class of problems which I call sequential decision making. These problems, they still exist. So these problems are not at all well solved even with modern MIP solvers. So these are, for example, vehicle routing problems, scheduling problems, some packing and cutting problems, some network design problems, especially when you have integration of network design with something else like vehicle routing. And the reason why MIP solvers are not efficient for this problems is that so we do not know good compact formulations for these problems which are strong enough, which produce strong bounds when the integrality is relaxed, even when all known families of cutting planes are added, which are generated automatically by MIP solvers. And so what we should do if we cannot solve this problems. What we should do, and one of the radical ways to improve the quality of formulations is to increase the number of variables in the models. So this may seem to be counterintuitive, but here you see in the picture that to describe the set of feasible solutions, if you have 2 dimensions, you need to have 8 constraints. But if you go to dimension 3, you need to have only 6 constraints. And so this is a way to reduce the number of constraints and to improve the strength of the formulations is to increase the number of variables. And what we usually do, we have variables which correspond not to a single decision, but the variables which correspond to a sequences of decisions. So several decisions at the same time. And to solve so the number of these variables is usually exponential, and that's why we need branching cut and price algorithms to solve it, because the standard branching cut algorithms which are used inside the MIP solvers, they are designed to be used when the number of variables is static, and when the number of variables is large, so we need to generate them dynamically. We cannot use branching cut algorithm and MIP solvers, and we need to rely on branch cut and price. So I don't have time to, of course, to present in detail branch cut and price, so I do it through an illustration. I would like to illustrate it with a well-known capacitated vehicle rising problem. So in this problem, what we have a depot with identical vehicles with identical capacities, and we have clients which are widespread over the plane. With each client has a different demand, and here I express demand with as a percentage from the vehicle capacity. We have a cost matrix, and we need to minimize the total traveling costs. We need to assign customer to routes to minimize the total traveling costs, such that we need to serve every client and the capacity of vehicles are satisfied. How to formulate this? So, if a way to formulate this problem, extended formulation with the exponential number of variables, we have 2 types of variables. We have what we call natural variables, so the variables which correspond to arcs in the complete graph, which represent the network of clients. So we have arc variables, and we have also extended variables. Each variable corresponds to a feasible route. And so we need to minimize the total traveling cost. So these are set conditioning constraints which state that each client should be visited exactly once. And then we have a mapping constraint. So we linking constraint when we link the natural x variables with the extended variables, and we have additional constraints which are number of vehicles constraints and the integrality constraint. Yeah, so this is a formulation with exponential number of variables. Of course, we will not solve it directly. We will generate this variable dynamically. And to solve the linear relaxation of this formulation, so we rely on the clone generation approach. So we will generate the variables lambda dynamically. So I will not talk here about how we do it. But the idea is that the algorithm, which is called pricing algorithm, which generates dynamically the lambda variables, need to be able to take into account these PA dual values, and so it needs to be able to optimize the sum of the dual values which come from this linking constraint. And so this is we continue the illustration. So this is the illustration of Coleman cut generation procedure. So here, instead of having integer variable per route, we have a continuous variable per route. And here on the illustration, I have a picture of a fractional solution where not the integer vehicles will go, but half of the vehicle. So each route here corresponds to half of the vehicle. So we solve this continuous relaxation, so the pricing is solved by elementary resource constraint shortest path problem. So okay, we do it, and then what we can do also when we end to solve the comb generation, we can still improve the relaxation by adding additional cuts. And one of the cuts we can add, so here you see that there are three clients in the bottom. The sum of the demands of these clients exceeds 100%. And what does it mean is that we need to have at least 2 vehicles which enter the set of clients. And we say that the number of vehicles which enter the subset of clients should be greater or equal to 2. It means that the sum of the arcs which enter this subset of clients should be greater than or equal to 2. And so this constraint is expressed in terms of the natural x variables, and this corresponds to so-called the robust constraint. Yeah. So generically what we have, generically we have again 2 types of variables: the original or natural variables, extended variables. So we have objective function, the constraint expressed over the natural variables, the mapping constraints between the natural and the extended variables, and some additional constraints. And so to improve the quality of the linear relaxation of this formulation, we can add 2 types of constraints. First, we can add a robust constraint, which I expressed over the natural variables. And this term robust, this comes from this paper. And actually here, robust has nothing to do with the robust optimization. So it's a totally different concept. And also, we can add the cuts which are expressed in terms of the extended variables, and these constraints are called non-robust cuts, and this term comes from this paper. And here you can already see that actually the term the concept of non-robust constraints, it depends on which variables we consider to be natural and which variables we consider to be non-natural. Yeah, because in different applications we can say we can declare a different set of variables to be natural. So the non-robust depends which variables are natural for us. And also another thing I would like to say here is that here the non-robust cuts also depends on the pricing problem, because so another thing I wanted to say that so why it is important to add non-robust cuts. So when as a main motivation to using branch and cut and price, in the beginning I say that we should use branch cut and price when the standard MIP solvers are not efficient, do not scale well. And in this case we can use branch cut and price, but branch cut and price will be more efficient than the MIP solver only if linear relaxation obtained by column generation is better than the linear relaxation of the compact formulations solved by the MIP solver. And not only better, it should be much better. Because if it's only slightly better, it will not pay off to use branch cut and price. And to have a better formulation, we can add cuts. But if we add only robust cuts, the disadvantage of robust cuts is that these cuts can be added both to the compact formulation and to the extended formulation. And so both branching cut and pricing cut will benefit from them. And so this will not usually help you to have an edge over the MIP solvers. But when you add non-robust cuts, these cuts cannot be added to the compact formulation without increasing a lot of its size, and so usually the non-robust cuts cannot be added to the compact formulation. And that's why when you use non-robust cuts, you have an additional edge over the MIP solvers, and in many cases, these non-robust cuts allow you to have to really have an advantage over the MIP solvers. And so now wanted to do an overview of different non-robust cutting planes proposed in the literature. I start with a small literature review. So it started. The pioneers were the work from Nemhauser and Park in '91. So they solved it. So they applied them for the edge coloring problem. So then the works for the cutting stock problems. A lot of works for the VRPs. And lastly, so it seems to accelerate recent years. So there are some works on the location routing, bin packing with time lags, temporal knapsack, and only in this ROADEF conference I marked 3 works which dealt with non-robust cuts. And so the message I want to pass here is that so in these 2 slides I put basically all works I know about non-robust cuts. So it's quite a lot, but it's not a lot actually. But maybe I forgot something, but I don't think I forgot a lot of works. And I think that there is still a lot of room to do research, to do additional research about non-robust cuts. And so now I'd like to make an overview of different ways to obtain non-robust cuts. And the first way, which is the most natural and not natural, the most common way is to do it by Schwartl-Gomery rounding. So the idea here is, I will illustrate it on the bipolarizing problem on the formulation I have just presented you. So you take this set partitioning constraint, so you replace the arc variables with the lambda variables in the set partitioning constraints. You relax this equality constraints to inequality, and what you do, and then you aggregate this constraint with some multipliers. So in this case, you take exactly 3 constraints which correspond to 3 customers, and you aggregate them with multipliers 1/2, 0.5, and then you obtain, then you perform Schwartl-Gomery rounding. So what you do exactly, so you take the coefficient of the lambda variables, you round them down. You can do it because it's less or equal constraint. And then as the lambda variables are integer, you can also round down the right-hand side and you obtain 1. So these are subset row inequalities which were introduced in this paper. So this is the illustration of when this inequality is violated, so it's the same fractional solution. Now we take a different set of 3 clients, and now you can see that you cannot apply the cuts we applied before, because before the total demand exceeded 100%. Here it does not exceed 100%, but here we can add the cut, which states that the number of the paths which serve at least 2 clients of these 3 should be greater or equal to 1. And so this type of constraint cannot be expressed with a natural x variable. So this is the really non-robust constraint. So these subset row inequalities were generalized to an arbitrary vector of multipliers by Piscine et al. So this paper here. And so what was important in this work, so they obtained the best possible multiplier vectors of size at most 5. Best possible means that these vectors and their permutations, their dominants means that if there exists a validated cut with different multipliers, there also exists at least one cut with one of these multipliers. And so this can help a lot with separation, because when you separate these cuts, you can just enumerate all these multipliers and you can do separation separately for all these multipliers. And so this is an illustration of the computational results on the CVRP, on the standard set of CVRP instances. So you can say that these non-robust cuts, they improve a gap a lot. So if with just adding the robust cuts, your gap is around 1%. By adding all arbitrary Schwartl-Gomery one cuts up to 5 rows allows you to reduce the gap from 1% to 0.17. So it's a large improvement. So the second way to obtain non-robust cuts, I call it the covering cut, and the general idea here is that in the problems when you have a set of elements to cover, so what you do, you take a subset of elements and you calculate and somehow the minimum number of decision sequences or columns which are needed to cover this subset of elements. So, for example, in this work by Neuhauser and Park, so here they consider an edge coloring problem. In the edge coloring problem, what you need to do, you need to cover a set of edges by a minimum number of matchings. And so what you can notice is that if you take a subset of edges which is an odd path in this graph, so to cover this odd cycle, you need at least three different matchings. And so you can add this constraint, and this will be non-robust constraint. So another type of covering cuts, these are strong K-path inequalities proposed by Baldacci et al. This concern the vehicle routing. And here they notice that the set of a customer should be visited by at least the total demand of this customers divided by the vehicle capacity and rounded up. So this is the minimum number of vehicles you need to cover this subset of clients. And this is very similar to the robust cut I presented you before, but here the difference is that there we considered only paths which enter the subset, and here we consider paths which visit the subset. So there is a slight difference between enter and visit. And here, so this can be illustrated in this picture. So you can see that there is a solid path which visits this subset of clients only once, but which enters this subset of clients 2 times. And because of that, so the strong non-robust cuts will be stronger, because the coefficient for this path will be 1, and for the robust cut the coefficient will be 2. And so there can be cases when the robust cut is not validated by this, but this strong cut is validated. And recently we did some experiments on the standard CVRP instances with covering with strong K-path inequalities, and we can say that these cuts, they really help to improve even the state-of-the-art algorithm. So I do not have yet the experimental results to share with you, but you can. So I can announce that these cuts, they really help to improve the branch cutted price for the standard CVRP. So to talk about another way to generate cuts, so I would like to talk about the compensated location routing problem. So here the difference with standard CVRP is that instead of one debug we have several debugs, and we should pay a cost to open a debug. And here this problem has a nice structure which is a nested knapsack structure. So because here each demand of each client contributes to 2 types of knapsack constraints. So the one type of knapsack constraints concerns the vehicle capacity, and the second type of knapsack constraint concerns the debug capacity. Yeah? And so the vehicle capacity is treated in the sub-problem, in the pricing problem, but the debug capacity is treated in the master. So in the master we have these knapsack constraints which say that for a particular debug the sum of the demands of the clients served from this debug should not exceed the total capacity of this debug multiplied by the binary opening variable. So this constraint, so we can, in order to generate cuts from this constraint, we can still apply Schlatter-Gomri rounding as before, but not only. So what we can do else? So to do something else, we need first to introduce some auxiliary variables which are TKQ. TKQ is the number of vehicles with load exactly equal to Q, which are routed from the debug K. And so then the form of the knapsack constraints will be like that. And so what we can notice that these constraints are very similar to the very known master knapsack polytope, which was studied in this paper by ROADEF et al. In 2003, and they did describe it how we can obtain the non-trivial facets of this polytope, and non-trivial facets they correspond to the extreme points of this system of linear constraint. These are the normalization constraint, complementarity constraint, and the superadditivity constraint. And so we showed in the recent paper that we can use the same extreme points which satisfy not 3, 4, and 5, but only 3 and 5, and these cuts are valid for the compensated location routing problem. So these cuts are not necessarily the facets for this polytope, because the condition 4 is not always satisfied, but they still valid, yeah? And they're still valid, and they can be useful. So these are results for some instances when all depots are open. So there are some variant when we decide first which depots to open and then to route. In these instances, we do not decide that. We consider that all depots are open, but all depots are still capacitated. And for this type of instances, so we compare 4 approaches. The BCP0 is the basic branch cut-in price. It's not basic branch cut-in price, it's the state-of-the-art branch cut-in price for the CVRP, but trivially generalized for the location routing. And about this branch cut-in price, we add two types of problem-specific constraints. So the constraints I have just presented you, these are non-robust constraints, and BCC as problem-specific robust constraints. And what you can see, and BCP best is the combination of all cuts, and you can see that these non-robust cuts, they really contribute to solving the instances faster. So they are really useful to solve the instances faster. And the last type of cuts I wanted to talk about are they concern the formulations when we don't have only leaking constraints, but we also have leaking variables. So here this is a simplified example when we have only 2 blocks of constraints, and these 2 blocks of constraints, they are linked by a set of leaking constraints, but also a set of leaking variables x0 here. And for this structure, in the very recent paper, which we just published this year, so the Claudia and al. They proposed what they call consistency cuts. So what they say is that you take this vector of linking variables, and you fix a certain value for these linking variables, which we call a pattern. And a natural constraint to add in this case is to say that the number of columns, the number of subproblem solutions from the first block which matches to this pattern should be exactly equal to the number of columns coming from the second block which also match with this pattern. So this is quite natural constraint, and this constraint, they have a nice theoretical properties that when the composition forms a staircase structure, and there are no leaking constraints and leaking variables are binary, actually these cuts are enough to obtain optimal integer solution. So we do not need any branching in this case. And so an application of this cuts, a nice application of these cuts concerns the so-called temporal knapsack problem. In the temporal knapsack problem, it's a generalization of standard knapsack where every item is active only during a certain time interval, and we have a knapsack constraints only for the items which are active at the same time. And here, so here you have the structure of the matrix of the coefficient matrix. So in the vertical axis we have the time. In the horizontal axis, we have items, and actually every vertical line it corresponds to one items. And here, what we do a temporal decomposition in time. So we divide the time horizon here, in this case, in four parts, and the variables in black, these variables are local to the parts, and the green variables they are linking variables because they concern several parts. And in this case, this problem has a generalization of the staircase structures. In this case, all the linking variables, they are active in the consecutive subproblems, and this structure is quite similar to the well-known total unimodular structure. And when the structure is available, we will have the same property that it's to obtain the integer solution of the problem. We need only these consistency cuts, yeah. And so we can, when we apply these cuts for the temporal knapsack problem instances, and we compare this approach with the other state-of-the-art approaches, we can see that we can really solve the problem instances much faster. So this is a very efficient algorithm for this particular problem, but the consistency cuts in general are quite general. They can be applied for any MIPS. So this is the overview I wanted to do, and now I want to talk about issues which may. So we saw that the non-robust cuts can be very efficient in practice. So they can really help us to solve many problems faster, but there can be some issues when one tries to work with them, and so I want to stop on three of these issues. So of course there are some other issues, for example, related to the separation, so sometimes it's very hard to separate, but I don't want to talk about now because of the lack of the time. So the first issue is that non-robust cuts they change the structure of the pricing problem. Yeah? And they can change in such a way that we cannot generate, because when we generate a standard robust cuts, we can generate them as much as we want. But here it's not the case. Sometimes we generate, and then the pricing problem becomes so difficult we cannot solve it anymore. And because of that, the family of non-robust cuts and the pricing algorithm, they are always interdependent. Means that the non-robust cut they affect the pricing problem, because the pricing problem should support non-robust cuts, but also the pricing problem affects non-robust cuts, because sometimes the pricing problem need to say that okay, there are too many non-robust cuts, I cannot handle them anymore, so please stop. And this information should be passed from the pricing problem to the cut separation. So there should be a two-way link between the separation algorithm and the pricing algorithm. And so what we can do in this case, so when the impact on the difficulty of the pricing of the non-robust cuts is too high, we can try to one of the ways to simplify that is to try to design a weaker variant of the non-robust cuts which are adapted for the pricing problem. And so one of the examples is the limited memory technique for the Schwatel-Gorley-Rachman cuts for the big pricing problems. And this limited memory technique is really adapted for to the case when the pricing problem is solved by the labeling algorithm. Means that if instead of labeling you want to solve the pricing by another type of the algorithm, so you should not use this limited memory cuts because they are not adapted at all. And this technique, this limited memory technique, so this was a really breakthrough for exactly solving the standard for exactly solving deep arousing problems. So the paper which introduced limited memory technique by Vecini et al., they got the prize as the best paper in the Mathematical Programming Computation journal, and I think this is a really good journal. So the prizes shows something, and so this is an illustration of the optimal solution of the last open instance, last closed open instance of the standard set of instances for the CVRP. And so this instance was first solved in this paper, and so Eduardo, one of the authors of this paper, he told me that he tried to, so if you remove many other techniques, many other state-of-the-art techniques from the branch-counted price, so if you remove NG paths, if you know what we're talking about, NG paths, enumeration, strong branching, and so on, you can still solve this instance to optimality in much longer time if you have this limited Schwarzschild-Montgomery cuts. But if you don't use limited memory technique and you use everything else, you cannot solve this instance even after a long time. So means that this for many instances this technique and the non-robust cuts are really necessary, absolutely necessary to attain the state of the art. So the second issue I want to talk about is about implementation. So I know that sometimes it's not easy at all to implement branch-cut and price algorithms, so it takes a lot of time, and in many cases people don't use branch-cut and price and don't use the most efficient techniques just because it takes a lot of time to implement, and they do not want to invest this time. And this issue is even worse when you use non-robust cuts, because when you use non-robust branch-cut and price, the implementation becomes even more trickier, even more elaborative. And so, but happily there are some tools which are available to help you with that. So one of these tools is our barcode library, which has been developed in our team for 15 years already. And last year, finally, we made the source code of barcode available for research purposes. And there is a user guide available, so you can go and try it. So to implement non-robust cuts, so it's not really that demanding. So you need to define only these four things. You need to define data structure which characterizes non-robust cut. You need to define, of course, separation algorithm, pricing algorithm, and only one additional thing you need to do. You need a special function which calculates the coefficient of the column in the non-robust cut. And the advantage of barcode is that it also provides you a lot of improving techniques for free, like stabilization, strong branching, column cleanup, and some primal heuristic which may make your branch-cut and price implementation more efficient. Of course, there are some other libraries which are available. For example, GCG, which is developed in the Aachen by Marco Lebeck team. And they also have some automatic separation of non-robust cuts, but there are not a lot of them. So only there is a subclass of Montgomery cuts, and they have also click cuts in future. But you can use these cuts only if the subproblem is solved by the MIP solver, which is usually not efficient. So of course you can use Skip, which is a flexible branch-cut and price framework, and non-robust cut implementation is quite similar to the one which you can do with barcode. But as I understand, the Skip does not provide you with additional techniques as barcode does. And also for Coluna is a branch-cut and price solver fully implemented in Julia, and we don't have support for non-robust cuts there yet, but it should be coming soon. And the last issue I want to talk about is the generality efficiency trade-off. So we noticed that currently there is a very large gap between the branch-cut and price research which is done in the literature and the practice, because in practice branch and branch-cut and price algorithms are very, very rarely used. So if you take the specific algorithms for specific problems, you need it seems that in practice you need a lot of human resources to support this kind of implementations. For example, there is a company called Jeppson in Sweden which does software for some airline companies, and their software is based on the column generation approach. And in order to support that solver, they have last time I checked, they have the largest operation research team in Europe. They have like 30 persons just to support the solver. Of course, you cannot afford having such a large team for for applications which are not that important as for airline industry. And on the other side, so there are some very generic branch cut and price solvers which are accessible quite easily, which are accessible just by modeling. But the problem that this GCG and barcode, they also can be used from just by modeling. But the problem is that when this BCP algorithm is very generic, the pricing is solved by MIP, and when the pricing is solved by MIP, usually you are quite far away from the state-of-the-art results. So usually the efficiency is not that good. And so what we try to, so in order to remedy to this gap, so what we tried to do recently, we tried to concentrate on so-called not specific, not fully generic, but what we call semi-generic branch cut and price solvers. And one example is the VRP solver, is the semi-generic BCP algorithm for the wide range of vehicle routing problems. And this solver is available just by modeling. So you just provide the model and you can use the solver. And the model is not the standard model, it's not the standard MIP model, it's a MIP and graph based model. But the interface is quite nice, and you can model a lot of VRP problems in 100 lines of code or so on. So, and the advantage of that is that it's more or less generic, and it also has a state-of-the-art performance for these problems. And the non-robust cards, we use non-robust cards in the solver to obtain the state-of-the-art performance. And these non-robust cards are activated just by modeling. So you can. So I don't have time probably to go into details here, but so we provide some special modeling concept in order to activate the usage of non-robust cards. So I will skip this slide. And finally, so just to repeat some takeaways you can take with you after this presentation. So the non-robust cards are quite often are really absolutely necessary to attain the state of the art and to outperform MIP solvers. So can be very efficient to improve the results and to do better than the MIP solvers. And this is actually a relatively unexplored area of research, so I cited a lot of papers, but there are actually not so lot of papers, and I think there are still a lot to be done in this direction. And the coordination with pricing algorithm is very important, because it's as I said, the non-robust card separation and pricing problem are interdependent. And happily, so there are some tools which start to appear now, which can facilitate the implementation, which can be really laborious for branch cut and price. And of course, for practical purposes, the generic approaches are especially welcome, because the specific approaches, they are very rarely used in practice. Thank you for your attention.
On a quelques minutes pour avant l'AG de la ROADEF. Oui.
Thank you for the presentations. My question is about the scalability of the current generation and non-robust cards. For example, if we consider semi-RP problems, if the graph size is about 500 nodes or 800 nodes, how much time do you need to solve the column generation at the root node? And how much time do you need to solve the column generation with cut at the root node? Can you compare this for large problems?
Yeah, recently we solved an instance, a CVRP instance with more than 800 customers to optimality with branch cut and price. Of course, it takes a lot of time, and usually if you want to have a reasonable time, you can solve instances up to 100 customers. And so if you have large instances, at the moment we're not yet there, but yeah, you can use heuristics, or you can use some clustering approaches when you cluster first and then you solve some problems. But yeah, up to 100 or 150, it's quite fast now.
Thank you.
Une autre question?
My question is, in case of a problem for which even with non-robust cuts, it's not possible to prove the optimality, do non-robust cuts improve the quality of the feasible solutions which are found by the algorithm?
Actually, we did not yet investigate this question. So yeah, usually non-robust cuts are really used to solve instance to optimality. So we still need to investigate how to use them if we just want to solve instance heuristically. So sorry, I cannot answer this question now, but maybe in 2-3 years, yes.
Une dernière question peut-être là, si on arrête parce que l'Assemblée générale de la ROADEF va commencer. Dernière question.
Thank you for the presentation. How hard is the separation of the cover inequalities?
Yeah, cover inequalities. So there is separation is not trivial at all. So there are some libraries available since a lot of time for vehicle routing problems called CVRPSEP. So they have quite a lot of algorithms, and more generally there is many variants of the k-path inequalities, and yeah, separation is not trivial, and it's usually you need to do research to find out how to well do it. So. But for standard problems, we know how to do it, but in general, it's still research to be done in this direction.
On remercie tous les orateurs et en particulier